Okay. Electron affinity. I've added a couple of extra bullets to this. Nonmetals need electrons to obtain a full outer shell. I guess that's a true statement. If the requirement is for a full outer shell, then they need to do that. I guess it's not a desire or a statement of desire, right? Because they don't have eyes and ears and brains and, wants. They have an affinity for electrons. Again, the term affinity sometimes can be thought of as, again, a desire. Oh, I have an affinity for dark chocolate. Who knows? Something like that. But I guess if electrons are just naturally attracted to those types of metals, and when I say naturally attracted, I mean a force of attraction, I guess that could be described as an affinity. So here's the term affinity as a representation of how it pulls electrons. Remember, when an electron gets pulled into an atom, it gives off some energy. It actually gives off a little bit of heat energy. It makes the atom vibrate a little bit. I kind of demonstrated that with my magnets. When the two magnets come together, it gives off a little bit of sound energy, right? It's a little, I guess it's a way of thinking of it. When the electron comes crashing in, it gives off a little bit of heat energy. So when an electron comes pulling into a chlorine atom, as it goes into that outer shell to fill it up, it causes that outer shell to vibrate a little bit. The whole atom vibrates a little bit. Okay. And this, again, is very repetitive. Our arguments will be exactly the same. So I'm hoping I can get through this in a fairly quick fashion. Trends in electron affinity. We're back to our, to our arguments. To be honest, I can't remember what the next slide's going to be, whether it's down or across, but let's talk about both of them. We could talk about electron affinity for the metals. I guess it's because nonmetals gain electrons, it might make more sense to come to this side. But we could talk about it for this as well. Just like we can talk about an ionization energy for these guys, right? Ionization energy for these guys, to pluck one away, what is it? Is it high or is it low? If I'm over here on this side. Emily? It's very high. Lots of protons, strong electrostatic force, hanging onto those things really tight. So we can talk about ionization energy for these guys, but they're not good metals because we need a low ionization energy. So I could talk about electron affinity for these guys, but I guess because we're talking about nonmetals, maybe we'll stick to this side, and we'll talk in a moment what it would mean then on that side. So even though we're talking about metals and nonmetals, you can talk about any atom in terms of ionization and electron affinity. So let's take a look at this row here, number 16. Oxygen to sulfur to selenium to tellurium, moving down the periodic table. What's going to happen to the amount of energy that is given off when an electron is pulled in to an outer orbit of those atoms? So we've got an electron that's out here. It's being pulled in, and it's going to crash into the atom. You can think of it almost like a satellite or an asteroid or a meteor crashing into the Earth. The meteor or asteroid is out there in space. It's going to get pulled in by gravity, and eventually it's going to crash into the Earth, and it's going to give off some energy because it crashes, right? What type of pull would be needed to have a catastrophic crash if we had an asteroid or something being pulled into the Earth? What would have to be true about the pull on that asteroid to have really catastrophic crashing? Yep. There'd have to be a strong pull on it, right? Now, for the Earth, the pull is determined by the mass of the Earth itself, so you can't really, tell whether it's catastrophic or not, because the pull doesn't change. But we can change the pull on an electron by looking at what's changing in the atom, right? So again, it's all about the pull. If an electron that's way out there is pulled in strongly, when it crashes, it's going to be a catastrophic addition of an electron, and it's going to give off lots of energy. If the pull is really weak, and the electron ends up in a place that's maybe way out there, like a big orbit, and it doesn't have a very strong pull to get into that big orbit, then it's not going to be as catastrophic, because it's going to come in slowly. It's a weaker pull. So our arguments are identical. We're again arguing the strength of the pull. Stronger pull, more catastrophic of an incoming crash, the greater the electron affinity. What happens as we move down the group? Yep, Natalie? It's true, the number of protons does increase. But there's another factor that dominates over the proton increase. Atlee's rethinking his argument. It's Monday morning, that's fine, go ahead. The number of orbits increase. Excellent. Would you like to keep going?
Basically, the outer orbit would be spread from.
Excellent. Good description. Keep going.
Like force of the protons in the place would be strong.
Perfect. The force on an electron that's going to come crashing in wouldn't be as strong. So how is it going to crash? Yeah, it's going to be a weaker attraction. And in our arguments, we're simply going to say, if there's a weaker electrostatic force, then the electron affinity is low, because it's not pulling as hard to bring that electron in. The pull on that electron is lower. So the electron affinity goes down as we move down the periodic table for the exact same reasons as before. All right? What about as we move to the right? Carbon, nitrogen, oxygen, fluorine. What's that going to do to the pull on the electron, and then eventually the electron affinity as we move right across the periodic table? Yep, Emily?
Well, the orbit number doesn't change, and there are more protons, so therefore the electrostatic force is stronger, and the pull is more, so the electron affinity is stronger.
Perfect. Full marks right there. Same orbit number, more protons, greater electrostatic force, pulls the electron in harder, greater electron affinity. All right? Greater electron affinity. Excellent. Very good. So, element with the highest electron affinity. Element with the highest electron affinity. Beware. Pitfall of a trick question here. Highest electron affinity. Where is it going to be? The one with the strongest pull on those electrons as they come in. Yep. Oh, no, it's not that easy of a trick question. Jeepers creepers, there is none. That's funny. That's okay. I set you up for that. No, we're not getting crazy. There is one. Where is it going to be? Yep. Hydrogen? Oh, that's funny. No, you were right with fluorine. Fluorine is correct. Well, some people might want to say this because it's further right and even higher up. Yep. Helium. Thank you very much. That's what I like to say. Would you quit saying that? I'm supposed to be saying that to you. You're supposed to be making the mistake, and I'm supposed to correct you condescendingly. Jeepers, you don't have it figured out. Very good. You had it right. Way to go, Chris. Good job. Normally, some people say helium, and I'll say, huh? Gee, what about its shell? Does it really want? I get to be condescending, right? He took all the fun away. He took the Monday morning fun away from the whole thing. Fluorine is absolutely correct. Helium is not correct. All right? Fluorine has one of the smallest orbits, all right, with a fairly large number of protons. It's not as small as these guys, but that guy's full, and that thing only has one proton. So a large number of protons in the row, fairly small orbit, right? A lot of electrostatic force. When the electrons come crashing in there, they come crashing in hard, and that gives off lots of energy, all right? Very high electron affinity, okay? Where are the atoms with a low electron affinity? Atoms with low electron affinity. No. Low electron affinity. Yep.
would think you would be hydrogen.
It's fairly low. It's fairly low. It's only got one proton. There's even lower. Yep. Yeah, again down here at francium. It's the exact opposite. You bet. Our best metals are down here, and our best non-metal is up here. And there's even a great dividing line that has an angle that splits those two extremes. Our stair-step line is on an angle such that it splits that extreme of great metal with great non-metal. All right? Yep, excellent. It is opposite. Let's write down some of our trends here. Oh, I'm getting rid of nuclear charge, folks. What am I putting instead of nuclear charge? Yeah, number of protons. Number of protons, just because it keeps things a little simpler. And I am a fan of that little add-on with the same number of orbits. I do really like that statement. Like as I teach year after year, at first I wanted it really complicated, and I found students really struggled with all of the steps, right, to explain this stuff. So now I've streamlined it, increased the number of protons. This increases the electrostatic force. This pulls the electron in harder. This increases the EA. But a couple of years back, I did have a student that was very good at always making the statement, same number of protons with the same number of orbits. And I really like that addition. Because as we move down, we increase protons, but the orbit number increases, and that has a huge effect. So I really like that little statement, same number of orbits, when you're making the argument for a cross. Okay. Really, when you think about it, our ionization energy and our electron affinity arguments are exactly the same. Low electron affinity doesn't want to pull on a neighbor's electrons. Low ionization energy doesn't even want to pull on its own electron. Something else could take that away. So they do the same thing. Low ionization energy, low electron affinity. High ionization energy takes a lot of energy to take an electron away from fluorine because it's got a strong pull on it. And if it pulls on a neighbor's electron, it's going to pull in hard. They do exactly the same thing. Low, low, right? Low, and high, high. But a good metal, a low ionization energy, makes it a good metal. But a good non-metal, a high electron affinity, makes it a good non-metal. So what makes them good are opposite. And that's why we have opposite parts of the periodic table. A good metal, low ionization energy. Yeah, I don't care about that electron out there. Go ahead, take it away. No big deal. A good non-metal, high electron affinity. If we were to attribute some characteristics to it, yeah, gotta have an electron, gotta have an electron. Right? An electron junkie. Excellent. There you go. Has a desperate need for electrons. Oh, maybe I should do attendance. Just 1 second, Jamie. I think we got one away. There you go. Thanks, buddy. So again, it's all about the pull on the electrons. The nonmetals have a strong pull. Okay. Non-metallic character. So across the period, for nonmetals, reactivity increases. More reactive. And down a group, the reactivity decreases. So again, the most reactive nonmetal, fluorine. All right? Okay? Again, we're restating the same thing over and over again. I'm hoping it's becoming, I don't know, easier, right? That we're seeing the same stuff. So you can now complete that electron affinity non-metallic character piece, but there's one more thing I want to talk about before I let you do some work, and that is something we call electronegativity. And again, our explanations become the same, but this is kind of a new, well, ionization energy and electron affinity have been a new concept, but this is a concept that becomes very important when we start to talk about bonding, all right? And that's what we'll be talking about after our test. We're just coming to the end of where we're talking about the atoms themselves and their individual properties, and next we're going to start putting those atoms together and discuss how those properties affect the way they bond. And so I need to introduce you to this term called electronegativity so that when we start to talk about bonding, that you understand what this is about. And hopefully you have your periodic tables nearby, because we're going to be looking for some numbers on the periodic table. You're going to be using these numbers in the future And I just want to introduce you to where to find that number, because as you know, that periodic table is full of all kinds of information. I'm slowly pointing out to you where the good stuff is, right? At this point, we've looked at things like the atomic number and the mass number, and now I want to point out to you, like I said, the electron affinity. Oh, sorry, the electronegativity. All right. Electron affinity is a measure of energy. We just did that. How much energy is given off when an electron crashes. Ionization is a measure of energy. How much energy is needed to take an electron away. Those are all physical properties that can be measured in the laboratory. Electronegativity is not actually a real physical property. It's a number that has been calculated by chemists that represents how good an atom is at sharing. Oh, isn't that nice? It's like a sharing number. So good, so nice. We always teach you in grade 9 and 10, either there's ionic bonding, right, where there's a transfer of an electron, some big bully of an atom takes an electron away from another one, and then there's covalent bonding, where they share, right? As if it's kind of, and everybody thinks, oh, those covalent guys, they're so nice. It has nothing to do with sharing. In reality, it's more vicious than that. It's really more of a tug of war. It's really more like two bratty kids fighting over the same toy. It has nothing to do with being able to share in any way. So let's fix that up. So let's talk about what this means. Chemists have taken the two numbers, ionization energy and electron affinity, and put them in a mathematical formula, which produces a number. And it's kind of a measure, like I said, the way it shares. When you have a bond formed between two atoms like chlorine and hydrogen, right? Chlorine's got its extra electrons out here, and it's going to have one of its electrons in this bond, and hydrogen's going to supply its electron to the bond. So these represent their electrons. And they supposedly share so they can get a full outer shell. Well, that's not really the case. If we talk in terms of ionization and electron affinity, both of these things have fairly high ionization energies. They don't want to give their electrons away. They're not like cesium and francium and rubidium. Which means when another atom comes along and says, hey, I want your electron, they're both going to say, no, I don't think so. I want my electron. High electron affinity. They also have, high ionization energy. They also have high electron affinities, which means when chlorine comes along to hydrogen and sees its electron, it says, I want yours. I want yours and I want mine. I don't want to share at all. I'm going to take your electron and I'm going to keep my electron. And hydrogen, because it's also high up there, does the same thing. Oh yeah? Well, I want your electron and I want mine. So in the end, the only way that they can be satisfied with getting electrons, if no one's going to give it up and they're both pulling on each other, the only way is to stand beside each other, right? You know, I don't know, I'm trying to think of a silly example of it. You know, somebody says, got your nose, right? Got your nose. Now you can imagine if that gets out of hand, there's some battle going on and somebody grabs the other guy's nose. And then the other guy does the same. Oh yeah? Well, I'm going to grab your nose. If they never let go of each other's noses, how do they have to get around? Kind of silly. But it's the same idea. Got your electron, right? Oh yeah? No, I got your electron. Well, I'm not letting go of my electron. I'm not going to either. All right, I guess we're stuck together. That's what a covalent bond is. Now, it turns out when the atoms are different, one atom is a little stronger at pulling than the other. And that makes the tug of war, all right? Take a look at your periodic tables, and I don't have a copy of it right here, but in the legend you will find that there is a location that gives us what is called the electronegativity, and it is near the top. It is to the right of the box, and it is above the name. Do you see the electronegativities? All right. So for hydrogen, what's the electronegativity? For hydrogen, what's its electronegativity? Yep. I think 2.2. I think there's a decimal in there. I hope there is. 2.2. 22. Wow, that would be like a muscle-bound hydrogen. That'd be like a super hydrogen. How about the electronegativity for chlorine? What do we got? Yep. 3.16. 3.16. What that means is that chlorine is a little stronger when it comes to hydrogen and pulling electrons. All right? And what that does is, in the end, when they go to share, they really can't share because they're pulling, right? It's a tug of war, and chlorine's a little stronger. So what that does is it pulls the electrons a little closer to chlorine. So the electrons are actually not equally shared. They're unequally shared. Again, I like to think of it as bratty kids fighting over a toy. If you've babysat, you've experienced this. Two kids fighting over one toy. I want that toy. You know, that's the way it works. And so you come along and say, fine, if no one's going to be able to share the toy, I'm taking the toy, and here's what's going to happen. You're going to sit there, and you're going to sit there, and I'm going to put this toy right in the middle so that neither of you can have it. It's equal distance between both of you, so there's nobody getting something better than the other guy, and you guys just sit there. And as soon as you turn around, what's one of those kids going to do? Grab it. And if you look back, they'll go, and they will have moved that toy a little closer to them so that they can say, I didn't do anything, right? So I like to think of the electronegativity being like a bratty factor for an electron. High electronegativity means it needs those electrons a little closer to it. If the electronegativity is low, I guess it's like that indifferent kid. Really? That's going to make you happy? Go ahead, man. Have a blast, right? In other words, not pulling back and not really having a battle for it. If you get two chlorines and they're both exactly the same, where's those electrons going to fit? Yep, right in the middle, because they're both pulling exactly the same amount. They got the same brat factor, all right? So electronegativity is a measure of how an atom pulls on electrons while they're in a bond, okay? What we talked about previously, ionization energy and electron affinity, it's just pulling on electrons, not while they're shared in a bond. So it's a bond kind of pulling number. We want to talk about the trends in this number, and the trends follow the exact same thing. As you move down the periodic table, the electronegativity goes down because it has more orbits and the electrostatic force is weaker and it doesn't pull hard on that other electron for the same reasons. As you move across, I'm changing nuclear charge. Hopefully you've already changed it yourself. If you haven't, it's not a big deal. I'm putting numbers of protons. And that's a little P plus there if you're trying to figure out what I'm writing. As you move across the table, same number of orbits, number of protons increases. It pulls on those electrons that it's bonding, and it increases the electronegativity. And when you're done writing, if you take a look at your periodic table, you can notice that. You know, if you go from, say, boron across to fluorine, you'll notice that number just steadily goes up. And then it stops. There's no numbers for the noble gases. Actually, that's not true. If you look down here, if you look down at xenon, right? Is it xenon or has krypton got one? These two noble gases have been forced to make some bonds. In the I can't remember if it was 30s or 50s. I don't know why I can't remember that. Chemists were able to make krypton and xenon form bonds with fluorine. Fluorine's super bratty pulling ability, right? You put that under really high pressure with some xenon and some krypton, and you can force those fluorine atoms to stick on and grab a hold and literally take away one of those electrons from, actually it forms a covalent bond. So they do have an electronegativity because they've been measured up against fluorine. Yeah. It's not that the noble gases are unreactive, they're of very low reactivity. The ones at the top are so small, they've got such a strong hold on those electrons, they haven't been able to make compounds out of those. But the bigger ones, they can. Radon is radioactive, it doesn't last very long, poof, it's gone and turns into something else, so they don't make compounds out of it. Question? Concern? Excellent. So that's the end of the trends that we need to know, all right? What I want to do just now before I let you start working, plenty of time here, you're going to got a great deal. You're going to be able to work on the rest of that worksheet, all right? And I'm going to give you the review questions that you then can work on in preparation for the test. Tomorrow is a review period, right? I think I've maybe mentioned that I don't do a review, right? But if you go home and work on review questions tonight and you've got questions set, then tomorrow's a great, time to take care of those questions instead of having to come in at lunch or that type of thing. So that's a great opportunity. Obviously, you can work on the review problems there as well. So you're going to have lots of time to do work. I've got one more thing I want to do, and I'm going to just use the Smart Notebook feature here. And I do want you to write this down. I want to simply summarize all the stuff that we saw. All right, I just want to put a summary of all these increase in this and decrease in that and all that type of stuff. And so what I want to do with this is I want to start by just drawing a blank periodic table. And you'd be surprised, it's easier than you think, right? If you take a look at the general shape of the periodic table, it's got a little step there and a little bump, and then it's got a couple of other bumps there. How can we help you?
That's 2 years, isn't it?
No.
Okay.
Sorry.
Please don't hold. Thanks.
Okay. So simply, right, draw a box that has like a bump, and then a line across here, and then another bump here, and then what do we got? One more bump at the top, and that'll do. And actually, I made it too far to the left. I'm going to clear the screen, and I'm going to do a new one. You can draw it up, but I'm going to do some writing here on the left, right? So I'm going to do some writing here on the side. So I'm going to start a new one. I'll put it more in the middle here. What am I doing here? Oh, pen. Oh, that's the worst table ever. What the heck is that? That's like a high chair. My goodness gracious. Terrible. All right, good. Beautiful, excellent. Okay, so let's just do some summary here. As we move down the periodic table, all right? So as we move down the periodic table, some of the stuff we talked about in terms of atomic radius. Does that make sense, atomic radius, the AR? You might have to write that down at the bottom, I don't know. What does the atomic radius do as we move down the periodic table? What happens to the size of the atom? It gets larger. And I'm going to just put an arrow up because I don't have enough room for increases, but I think we get the idea, right? The atomic radius increases as we move down the periodic table. We talked about ionic radius and we compared ions and all that type of stuff, but we didn't really compare trends of ions. If you're talking about stable ions, as you move down, they get bigger as well because they get more orbits as well. So we're not really worried about that type of thing. The next thing we talked about was the ionization energy, the amount of energy needed to pull that electron away. What happens to the ionization energy when you move down the table. Yeah, Janessa? The ionization increases. It's going to become harder to take those electrons away as we move down the periodic table. It decreases because they're getting larger and they're really easy to pluck away. It decreases. Excellent. All right. Now, down here on the bottom, just before I talk about the next one, which is metallic character. For a good metal, what kind of ionization energy do I want? It's a good metal. Yep. Low. Low IE results in a good metallic character. They're opposite, right? Low ionization energy, don't care about my electron, fabulous metal. So as we move down, the ionization energy decreases. So what happens to the metallic character? It increases. It's the opposite. It does the opposite. Right? Okay? And we can do the same for electron affinity. Electron affinity. What happens to that pull on that electron as it comes in as you move down the periodic table? Atoms are getting bigger. It's still a pull. It's just a pull on the neighbor's electrons. Makes a difference. Same trend. What happens to that pull? It decreases. Ionization energy in electron affinity is the same. Not only does cesium not care about its own electron, but it doesn't care about the neighbor's electron. No pull whatsoever. Okay? This is kind of a silly thing to say, but if the metallic character increases as you move to the bottom where you've got the rock star of metals down here in the corner, what's going to happen to the non-metallic character? The non-metallic character, yeah, it's going to decrease. You cannot have a good metal and a good non-metal in the same spot. It just makes no sense. The reason we can say that is for a good non-met, because just to put AL on the end would be way too much work. When you make study notes, you want to make things tiny. For a good non-metal, what's true about the electron affinity? It's high. High electron affinity results in a good non-metallic character. It's the same, where the other one is opposite. Okay? So let's work our way across then. Across the table. If you don't have room above, you could put all this information underneath. It's still working its way across. And I'm simply going to go through all of these same, things that I just talked about here. Atomic radius. What happens to the atomic radius as we move right? I'm going to pause. Emily's arm must be tired. I got multiple Emily's here. Hands up, Chris. Across the row in the middle here. Let's ask Connor, what do you think? What's going to happen? What happens to the pull as we move to the right? It increases because there's more protons. If there's a greater pull, what's that going to do to that outer orbit? Make it smaller. So as we move right across the periodic table, the atomic radius actually decreases. All right? Let's talk about non-metallic character before we go back and talk about this. So I'll just move over here. Let's go with electron affinity. EA. What happens to the electron affinity as we move right? Yep, Jerry? Increases. More protons, stronger pull, increases. And if it increases, therefore, what happens to the non-metallic character? Yep, Emily? It increases. So our good metals are up here in the corner. Excellent. And we can do the same argument with the ionization energy. What happens to the ionization energy as we move to the right? Yep, Jory? It increases, right? It's a stronger pull. Stronger pull increases all that stuff. Increases. And then, how is our metallic character over here? How are these as metals? Jory? Decreases. They're really crappy metals. They're so crappy we call them non-metals. It's true. I'm just saying. All right? Okay, so there is a summary of all the things, right? And again, I guess it all comes down to this. As we move this way, the electrostatic force increases, right? And that's the thing that we argue, right? This has to do with the fact that we've got more protons, right? There's the whole argument. When you make study notes, you want to make things short and sweet so that when you start, memorizing it, it's easier. But when you move to the right, the electrostatic force increases. That increases the pull on other electrons. That increases the pull on its own electrons. As you move down, we've got here more orbits. And what does the electrostatic force do? Electrostatic force decreases. All right? So there is a little summary of it all, and it's all about the forces. The only thing we came across that we couldn't argue orbits or protons was the formation of the negative ions, the anions, and the more electrons you put in it causes an increase in repulsion, and that makes the anions bigger than the neutral atoms. It was the only one we couldn't use that for. Okay, so let's go back to the PowerPoint, and let's bring, that's all good. And there is the chapter review questions out of the textbook. You have the rest of that trends in the periodic table sheet, right, which essentially is the non-metal stuff that we did today. And then, like I said, practice problems.